graph of a relation is illustrated in this example, in which we have relation R defined using set builder method as shown here. So R is a relation defined by this set of two tuples with elements x and y, such that x squared plus y to the power 4 plus 2 times x times y squared is less than or equal 37, and the domain is the domain of natural numbers, or basically non-negative integers, 0, 1, 2, 3, and so on and so forth. So the first thing we need to do, one further quick simplification here, is going to help us, which the way that this is written effectively represent x plus y squared to the power 2 is less than or equal 37, which effectively means that x plus y squared should be less than or equal 6, because 6 to the power 2 becomes 36, and that's still less than or equal 37. But anything above that will not satisfy, because as soon as this number becomes 7, then 7 squared becomes 49 and doesn't satisfy this inequality. So following this guideline, following this requirement, let's just list the two tuples that belong to this relation R given the domain of natural numbers. Okay, we are going to use just brute force raster method. So I am going to just purely list the two tuples that exist in this relation. So first one, of course, is 0, 0, because that does satisfy this. Then you can see that 0, 1 also works. 0, 2 also works. And remember, the first one is x in the two tuple, the second one is y. So 0, 2 means 0 plus 2 squared, which is 4, and it's less than or equal 6. 0, 3 doesn't work, because 0 plus 3 squared becomes 9, and that does not satisfy this. So we have to move on. We have to move on to 1, 0. That works. 1, 1. That works. 1, 2. That works, because 1 plus 4 is still less than or equal 6, but 1, 3 doesn't work. So we have to move on to 2, 0. That works. 2, 2, 2, 1. That satisfies this requirement. We have 2, 2. That also satisfies this requirement, because 2 plus 4 becomes 6, and still 6 is less than or equal 6. It works, but nothing above that. So we have to move on. 3, 0. That works. 3, 1. It works. Because 3 plus 1 is 4, and 3, 2, it doesn't work, because 3 plus 2 to the power 2 becomes 7, and that does not satisfy this. So we have to go to 4, 0, and 4, 1. 4 plus 1 is 5, but 4, 2 doesn't work. So next one is 5, 0. That works. 5, 1 also works, right at the threshold, because it becomes 5 plus 1, 6, and the only thing that works with 6 is 6 and 0, nothing else. So this is the raster method of representing this relation R. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So effectively what we found is the cardinality, or the size of this relation, number of tuples inside this relation, is 16. And as you can see, if I want to form the digraph or directed graph, so form the digraph or directed graph, I have to include all the vertices or nodes, and also all the 16 edges or connections. So you can see 0 and 1, they have central roles in this digraph. So just for the sake of better illustration, I am going to say use the red color to represent my vertices, and for that purpose let's just say this is 0, or let's say, yes, this is 0, and let's say this is 1, and of course we have 2, 3, 4, 5, so let's just distribute them around, and you can see that 3 and 2 are not connected to 4, 5, 6. So maybe just for the sake of better visualization, let's have, I don't know, 2 here, and then let's have 3 here, and then let's have 4, and let's have 5, and 6 is sort of a isolated node or vertex, because it's only connected to 0, so I can easily just put it here. Say here. It doesn't matter that much. Okay, now the connections. So for connections, all I have is 0 to 0. So there is a self loop on 0. That's good. Okay, so this is 0 to 0, self loop. And then we have 0 to 1. So we have a connection like this. Okay, and then we have 0 to 2. So a connection like this. That's an edge. Then we have 1 to 0. So that means a connection back. So 1 to 0. So it's a two-way or bidirectional connection. And then we have 1, 1. So that means a self loop on 1. Okay. Then 1, 2. So we have this connection. Okay. And 2, 0. So we have a two-way connection here. 2, 1. So there is a two-way connection here as well. Then we have 3, 0. So let me use a different color. So there is this 3, 0. So maybe just for the sake of better visualization, I just do it this way. 3, 0. Okay. And then 3, 1. So 3, 1. 4, 0. 4, 1. 5, 0. 5, 1. 6, 0. As you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Am I missing one? So 0, 0, 0, 1, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1. Yes, I am missing one, which is the 2, 2. So the self loop on 2 is missing here. Okay, so here's the self loop on 2. It's always a good idea to double check that you're not missing an edge or a vertex on, of course, vertices should be there, all the vertices. So you need to make sure that they are properly indicated. Okay, so this is our digraph. There are, as you can see, there are 1, 2, 3, 4, 5, 6, 7 vertices or nodes on this digraph, and there are 16 edges as is shown. I hope that this example is helpful to show how a relation defined by a set builder can be then mapped to a visual representation in the form of a digraph.